Welcome to Utilizing Tech, the podcast about emerging technology from Gestalt IT. This season of Utilizing Tech focuses on Compute Express Link, or CXL, a new technology that promises to revolutionize enterprise computing architecture. I'm your host, Stephen Foskett, organizer of Tech Field Day and publisher of Gestalt IT. Joining me today as my co-host is Craig Rogers.
Hey, Stephen. Great to be here. Looking forward to getting a chat with Hasan around CXL and memory tiering, at that software layer in Linux. What about you?
Yeah, that's where we're going to go, Craig. Essentially, we've been hearing recently that now that there are some CXL supporting platforms out there and some devices that can be tried out, we're starting to see some numbers, and the numbers look pretty good. The summary is that a CXL memory expansion card looks a little bit like a memory on a remote NUMA node, or maybe even a little bit better than that. But that being said, there's going to be much greater latency once the memory moves onto a fabric and gets into a shared pool and maybe even goes remote, like we talked about with IntelliProp. So we really need to start thinking about how to handle this idea that there's different kinds of memory. There's different tiers of memory with different performance. And so that's why we received a tip that we should invite Hasan Al Maruf to join us here. Hasan is a researcher at the University of Michigan focused on transparent page placing, which is really a great and important way to enable the use of tiered memory. Welcome to the conversation, Hasan.
Hi. Hi, Stephen and Craig. It's nice to meet you.
So tell us a little bit more about your background. How'd you get into this?
Yeah, sure. So I'm a PhD student at the University of Michigan. I'm at the end of my PhD. So my research focus is mostly on data center resource management and performance optimization. It's mostly on resource disaggregation, heterogeneous tiered memory management, and recently on CXL systems. So you can say, in a word, my whole PhD is like how to make memory disaggregation practical. I lead a comprehensive solution to address the host level, network level, and end-to-end aspects of practical memory disaggregations. How we can hide the latency during memory disaggregation, how we make it like fault tolerant, how we can actually make it more efficient and ubiquitous. And recently with CXL systems, there's tiers of memory could be there, and how we can handle those things. And mostly we focus on making these solutions transparent to the applications so that existing or newer applications can be like have benefit of this memory disaggregation. And you can say like whatever challenges comes to make memory disaggregation practical, uh, me and our lab kind of focused almost all of these aspects over the years. And it's very I was like very opportunate highly opportunity to like work with Meta and get access to like CXL devices and do something that could be like open sourced and merged with Linux over the time. And so this TPP you are talking about is like transparent memory page placement for CXL systems. This is the like new additions in our work. And yeah, and we are thinking of many more new angles of CXL enabled systems, how to approach them from the software area. And yeah, that's it in a very few words about me.
You mentioned a really interesting turn of phrase there around hiding latency. One of the biggest concerns people will have with large scale adoption of CXL is not just the cost in adding in more RAM, but also the performance, and latency is one of those key metrics that people are looking at. Can you go into any more detail around how you're able to hide that latency?
Yeah. So my very first PhD project was Leap. It was like how like at that time when I started in 2017, there was like RDMA enabled InfiniBand networks. That was the fastest network possible available there, which is like microsecond scale. So in that case, with this InfiniBand network, you can connect two different servers, and one server can access the memory of another in microseconds. So even if you remove all the software overheads from the OS, still the network is around 3 to 4 microsecond for a 4 kilobyte page. So you cannot like break the physics, right? So what you have to do normal case, CPU attached memory is hundreds of nanoseconds latency, and in RDMA enabled area it's like microsecond scale. So you have to somehow hide this latency by doing some prefetching or some intelligent systems. So this leap is like enabled a kernel in the kernel in kernel prefetching mechanisms for remote memory or disaggregated memory things, and that could like make almost provide hundreds of nanoseconds of latency till 95 percentile, and rest of the percentiles we had to go around microseconds. With CXL this microsecond comes to like around 300 or 200 of nanoseconds, but it's still like higher than like hundreds or 200 nanoseconds higher than the normal local CPU attached memories latency. So in TPP, we had some approach so that like our main approach was like whatever is hot, they should be in the CPU attached memory, and whatever is cold or warmer, we can like handle the extra latency access could be put into the like lower tiers of memory, slower tiers of memory that is attached to the CXL. So that was one approach. While where whatever is hot, always try to move them to the hottest tiers of memory level. But this is also a reactive approach. Whatever we have in the TPP, this is the state of the art, but still it has some scope of improvement. Some prefetching could be applied here. Some other mechanisms could be applied here to make it even more faster. So yeah, so right now the best approach is like whichever is hot, always try to allocate or bring them in the topmost tiers of memory, and that can like reduce a lots of slow tier memory access, and you can effectively hide some of this extra latency of CXL memory.
Yeah, and we're not talking about caching here. We're talking about basically having the software intelligently move pages of memory based on the characteristics of that page, the accesses to that page. So,
Yeah.
if it's something that's being used quite a lot, quite often, you put it in the memory that's closest to the CPU.
Hmm.
And if it's not used very much, then you put it in a different tier. And,
Yeah.
and and it sounds like this would make sense. Like you said, you've got InfiniBand-connected RDMA peers. You've got other kinds of memory tiers as well. I mean, we've heard quite a lot about Optane memory, persistent memory from Intel, which Intel just announced the third generation along with the Sapphire Rapids platform. We've talked about CXL connected memory and even NUMA memory. I could imagine that TPP might be viable even in a conventional, just a NUMA system where you've got some memory that's close and some memory that's a little bit further away.
Yeah, you are absolutely right. So basically, in TPP's world, although it's designed for the CXL systems, but it could be like generic to any kinds of NUMA systems. So when you attach a CXL memory devices, it appears to the OS as a new NUMA node. So if we can support for different NUMA nodes, how page placement for different types of NUMA nodes, that will be obviously applicable to any CXL systems, and that's what we did in TPP. It's like when you have to like allocate a page, you try to allocate the most hot pages in the very faster tiers of nodes, and over the time but you cannot always do these things because your CPU attached memory has some limited capacity. So at some point, if everyone is hot, you have to like move some things at some other layers, right? So it's like TPP is the solutions what gives you whatever matters the most, they will always remain on the topmost layers, and these warmer or colder portions that will be efficiently migrated or efficiently moved to the lowest part, so that this reclamation does not impact your allocation. Because in today's OS, whenever you need to like allocate, you have to find whether there's enough memory in the topmost tiers or not. If not there, then you will go to the by default it will go to the next available memory tiers, and when you allocate in the next available memory tiers, it will be all like even in a two socket systems, it will have extra 60 to 80 nanoseconds just for accessing a memory of the second socket or the remote socket of the CPUs. So that's why we had faster demotion path, and we have one very optimized promotion path. In the demotion path, we demote so fast that always there is always headroom in the topmost tier, and new allocations can happen over there. And in the promotion, wherever someone becomes hot again within the coldest part, they could be like optimized way, they could be like bring back in the systems. And not every brought back page could be utilized there. Like you can say some pages could be cold and accessed within once in an hour, and if you bring that, if you like mistake them as a hot page and bring them back into the like topmost tier, then eventually it will be colder again, and you have to like demote it back. So this will be some wastage of bandwidth, wastage of CPU cycles. So we need to be more accurate about what we are bringing from the colder tier to the like hot tier. So this all these things are covered by the TPP. They like consider at which point which pages could be like a promotion candidate, and what will be the benefit of moving them from coldest tier to the topmost tier. So yeah.
And you guys submitted, or I think you submitted a kernel patch to Linux a couple years ago in 2021. Is that in the kernel now? Is that something that's out there?
There's basically two patch sets. One is like all the basic things of TPP. There's some performance monitor, how much anon or anon page, different types, anon page types or cache page types, how much has been like promoted or demoted. What's the rate of this movement, what's the failure of page migrations or promotion demotions. That's one thing. Another is like we added new watermark systems. There's Usually there was like high low mean watermarks. We added another extra watermarks over there. Then we made this demotion path, how faster we can do this. There's another patch over there. And also during this promotion, we modified the autonoma. So right now autonoma has different modes. One is like for vanilla and another is like for tiered memory systems. So for this tiered memory system, this TPP will work and do these migration stuffs or promotion stuffs. So that's one thing. There's basic TPP approaches which will be generic, and there are some another patch set that is like for specific to applications. Like you can say some applications use anon pages, some applications use cache pages. So let's say there one application is not sensitive to the cache, but during the boot up it allocates most of the file pages, and those file pages consume most of the hot tiers of your memory, most of the memory of your hot memory tiers. And when this anon comes, which is very much sensitive, they have to like eventually allocate it to the like lower tier or slower tier. And then you have to like promote them back to the topmost tier, or you have to like move you have to like bear this latency of the CXL memory access. So there's like page type aware allocations. If we say okay, for this application cache is not that much sensitive, from the very beginning of the application runtime all the cache will be allocated to some slow memory tiers, and all the anons will have the all topmost or highest priority in the topmost tier. That's one patch set. Another is like interleaving. So right now in NUMA, when you do interleaving, every NUMA node is of similar behavior and they consider them of same value. So one interleaving is it will like do round robin. If you have three nodes, it will one allocate one by one. But in CXL world, different NUMA nodes may have different characteristics. Some may have like high bandwidth, some may have like high low latency. So based on different NUMA nodes behavior, we can set the weight of interleaving. So maybe topmost tier can have like 10 pages that will be followed by 2 pages in the slowest tier. So that there you can like set the ratio how much of the allocations can be like on different tiers of the memories. So this is another patch set. So these two patch set has been like published so far. Among them, like the generic TPP has already been merged in Linux version 5.18, and these interleaving or page type aware allocations policies, those are yet to merge because those are very specific to like different applications. And Linux community is always they consider whatever is generic, they should be like merged first. So if it's not that much generic, it's very hard to convince people okay this should be go there. So but we are very much hopeful these things will be merged pretty soon, the page type aware or applications aware policies. But the basic TPP is already been in Linux kernel.
It's interesting what you're describing there. That tiering. If we throw back to the storage world, You'd had early storage devices, SANs, that would have had an SSD caching layer for hard drives, whilst we're miles apart in terms of latency and throughput. With tiers of memory, the functionality level is the same, where you're keeping hot data on faster storage. It's more readily accessible. But normally those are proprietary type products that provide that level of functionality. You're talking about this being integrated into the Linux kernel itself and making those decisions around the tiering. That would have to be observable. There would need to be evidence as to how that was being used and address. So, how can Linux people observe that? Monitor that and report against it.
Okay, so far in our TPP patch, there's some basic monitoring, but this is not the wholesome monitoring. Some monitoring is like when we are reclaiming, what types of pages we are reclaiming, what's the rate of reclamation. So then you can say, okay, these are the specific types of pages that remains cold over time, and for that they are going to like move to somewhere else. And when we are promoting, what types of pages has been promoted, what's the rate within times, how much has been what types of page has been promoted at what granularity, that can be seen over there. And during migrations, if something fails, what is the like failure reasons of the fail, where it's failing, which node is failing. So these very basic observations can are available today with like TPP, but that's not enough. You need to like know what's the application's behavior, and for that maybe you may not modify the whole Linux kernel. You may need like some different tools. So we have in our project, like in Meta, we have a tool, it's called like Chameleon. It's not still open source, but we are very hopeful to open source it within couples of months. So that tool is useful for monitoring. So here you can see when you run an applications, you can see what's the behaviors of this application's memory access pattern, how much of what chunks of its memory has been hot within a different time period. Like maybe you can say within 2 minute time period, 20% of this application's memory remains hot. What is the reaccess granularity of a page? Maybe within 2 minutes, this page has 80% of its pages has been reaccessed. So that means most of the pages are being touched over time. And like um, what is their temperature, like you can have a heat map, I can say. So and that can be used. There's different approaches to doing so. One can be like using Linux kernels, page access bit tracking stuffs. There could be another things like PEBs based stuff supported by Intel. For AMD's processor, there is another ABIs. So with using these counters or CPU counters, you can have some idea, okay, for these particular applications, this is its memory access behavior. And if we consider this behavior, whether this application is applicable for the traditional setups or it can be moved to the like CXL world. And if we move to the CXL world, how much performance loss we can consider. Things are like with CXL, you have to bear the latency bottlenecks. So there should be some performance dimensions over there, but how much performance dimensions we can have. And if we can very intelligent in moving right portions of memory at different tiers, maybe we cannot have this performance bottlenecks. Like in Meta, we find like uh, even if we support only 20% of the whole working set into the topmost tier, we actually reduce the topmost tier to 20% of its whole working set, and 80% could be like in the CXL tiers. We find we lose only 5% of the performance. So you can know these things by characterizing these applications. So this kind of tools we already developed is about to be like open source. If the paper is published, it is easy to like open source the stuffs, because in the Meta you need to know, like there's a lots of reviewing process whether we should publish it or not. But there's another company like Memverse. They have already a product like MemViewer. This can also be useful to understand the same kind of things. So yeah, so I think like the basic Linux, it should have some uh, counters, it should have some monitoring systems from the very basic thing. But in the Linux, you cannot have this freedom of doing everything. So there should be some user space tools, and with CXL switches, there will be more counters. So using those counters, you can see, okay, this specific node has these amounts of load, heat, miss kind of things, and based on that, you can come up with another tools for monitoring what's the memory access behavior at different layers or different nodes or different devices. And yeah, from there you can have a more robust and more strong characterizations of applications. And
So I'm glad that you brought up the meta results, because I know that that's been another thing that you've done, is you've done some benchmarking, some work characterizing the performance of transparent page placement, and it's really pretty positive. Like you said, you don't have to have the entire working set in the hottest tier of memory. You can do it on a page by page basis. You showed there some serious performance improvements by implementing this. Do you think that eventually this is? I mean, we've been sort of assuming that tiered memory is going to be a normal part of compute architecture going forward. Do you think that eventually transparent page placement is just going to be something that the kernel does, and people aren't going to? It doesn't have a name anymore because it's just something that's on, and you just use it.
yeah, why not? Like, if you consider, like, in today's in the NUMA systems, you are basically doing some kind of page placement, right? So what's the difference with the CXL? Like, it's the complicated NUMA systems, right? um and you have to do some page placement for these types of things. Today's NUMA systems is everyone is homogeneous, and future NUMA systems would be like heterogeneous NUMA systems. So there should be some support for heterogeneity perspectives, and TPP is the stepping stone for this heterogeneity. So there could be like many more improvement over it. Like, when you, like, in TPP right now, we are like demoting the next possible NUMA node, but you, with a very large, with switching with CXL 2.0 or 3.0, when switching is available, multi layers of switching is there could be like GFEM, there could be like some other like type 2 types of devices could be there. So in that case, which layer or which specific NUMA node could be useful for these applications. Like, not always having the topmost tier is helpful for the application. So if you consider multiple applications running on the same systems, and everyone has different demands of their performance, in that case, maybe next top tier can be helpful, even to maintain its performance, desired performance. So in that case, which tier you can choose, or what fraction of which tier is enough to provide the performance benefit of these applications, that could be a good challenge, and we are working on that. And I hope like it could be like easily, or there could be like many more challenges that can be like approached, and people will work and already working on them. And obviously there will be some of them will be merged to the Linux, because everything, the whole industry is moving at that area, so you have to like have some support somewhere.
The Linux community have always been very good at baking in a lot of kernel support for a lot of hardware solutions. Are you seeing other areas of the Linux community contributing anything else around CXL and memory tiering? Because knowing that technology is going this direction, it's one of these things that will benefit all the users of Linux and all the contributors.
See, so like just as I said before, what is like memory monitoring tool, like what is the work sets behavior? Already there's a patch set been merged with 5.15 Linux. It's like from Song Yangju from the Amazon. It's like daemon, the call to is daemon. So it's like for a specific workload, what fraction of is like hot cold stuffs that's already been you can have some view of this world. So that's already been there. I know in the like Samsung, they are doing Samsung Ghost Team, they are doing some very good works, or they have some work in the pipeline to support CXL ecosystems. There could be like these auto healing stuffs, or these resilience stuffs. Like earlier, everything was within a single machine, and now we are going beyond a single machine's domain. So any machines can fail anytime. You need to support, provide, like your main memory is can be like unavailable at any time. So you have to provide some resiliency for that. People are working on that area. And like memory sharing, sharing consistency, coherency management. So these things are being like addressed, and I think the whole industry is working on different aspects of these problems. And maybe within a 1 or 2 years, I think there will be lots of patches being merged in the kernel, and maybe CXL will be very ready to use by everyone by maybe end of 2023 or 2024. So
Yeah, and I think we also have to give credit to Intel for doing a ton of the basic plumbing for CXL within the Linux kernel. I know that they've submitted, and they just keep submitting more and more and more, including recently a bunch of support for Type 3 memory in CXL. So I think that it's great to see so many people contributing to the development of the Linux kernel, because of course, well, a lot of systems out there. I think probably an easy majority, if not a vast majority, are going to be running Linux at this point. Though, as we've talked with other companies, I mean, we talked to VMware. They're certainly planning on having a lot of CXL support as well. But I mean, right now, Linux is really where it's at. Does that match your opinion, Hasan?
yeah, so I think like everyone is trying to build the whole ecosystem so that like it's open to all, everyone can like easily use it. And I think m- almost all the big companies are like focusing on how to do stuff, make them open source, and make it even more usable by everyone.
So it sounds as though the community are contributing to empower the proprietary solutions they need to build to do advanced monitoring, advanced memory tiering solutions, but they're building in the mechanisms within the kernel space so that they to facilitate their user space requirements.
So some part, there should be some mechanisms that is fundamental, like these placement stuffs. Without modifying the OS from the user space, you cannot do much. Like, let me share my experience. So when in the Matters project, initially we tried with this characterization tool. We found, okay, these are the different heat map of a specific applications, and from that heat map, why not we do this memory management on in the OS level, in the user space, from the user space. So the problem of here there was like, um, some memories or some pages, they are very short lived, they comes and go. You cannot like by the time you decide, okay, these are the pages we need to like migrate, those pages has been gone. And from the user space, you need some user to kernel space movement, context switching, that can takes time. And you don't have that much freedom of work. So that's, from that point we decided user space solution may not be sufficient. We need to modify the kernel and build, apply these specific things from the kernel, so that it could be easy, it could be faster, and it could be like generic. And that's why even we have the freedom of doing everything from the user space, eventually we have to went to the like Linux kernel and need to like modify this. And I know some cloud vendors in the hypervisor level, you can say, so they don't have the opportunity to like understand what the application is doing. So maybe they are completely oblivious what's the behavior of the application. They have some idea what is doing over there, but per page wise idea or tracking per page can cost them much high latency. So from their perspective, modifying the hypervisor could be like the best options to like go on. So there could be some solutions that can work in the hypervisor level. And yet, like, let's say you have some very intelligent mechanism, you want to run some ML stuffs. Let's say you run some machine learning algorithm to understand what is the application's behavior or what's the other properties. And that ML applications, you cannot like integrate it with kernel, because it will be too much heavyweight if we run some MLs inside the kernel. So for that, you need some user space tool, or you need some other mechanisms that can like communicate with the kernel. So uh, based on your use case, based on your requirement, I think different solution is needed at different layers. And they could be like communicate with each other, it could be like completely independent solutions. And I feel there's also some room for proprietary solutions, and there's some fundamental stuff needs to be done inside the kernel, which is like Intel's, Samsung's, or some other companies are doing. So
Have you observed much of an overhead in tracking these page values. If you're tracking heat, there's obviously an overhead to that. Is there a point of inflection?
uh, Whenever you are tracking, there will be a overhead. Like let's say we are tracking by these idle bitmap stuffs. So in that case, you have to like set and reset the page one page flag of every pages over there. And if your working set size, let's say it's terabyte size, then you have to like frequently modify the bits of all the pages within a 1 terabyte, and it will be like tremendously high overhead. So that's one reason why we did not go in the like page track idle bit tracking way. Then we found, okay, Intel CPUs gives PEBs, PMU is available there. So from there we can have some CPU counters. Let's just do sample from the CPU counters and come up with there. But even when you're using the CPU counters, you need to like burn some CPU cores to get these numbers and parse them, and then actually get some analysis. So that's another reason, like this PEBs based tool or this counter based tool that has not been uh, in the kernel side. We did not go that route, because if we from the kernel, if we use this uh, CPU counters, we will lose the freedom from the we will have less counter available in the user space. It will halt the CPU every now and then. And if the workload is very much CPU heavy, maybe your monitoring system will halt every now and then, your application may crash. So that's why we separated this as a like two separate tools. One is for characterizations, you can run it every now and then and halt it every now and then. And another is like very basic thing, always running within the kernels. So two different tools, one is characterization tools, another is like Linux kernel modifications of page placement. This is very basic. So yeah, the overhead is very high when we run these chameleon tools. It we found like for a very heavy workload, it is around 10% of slowdown. And there are some other works available where they showed like in IPT based case, you can have 20 to 90% of overhead based on the workload behavior. So whenever you're running these things, you have these overheads. And even we in TPP we used autonoma is, you have also some kind of like faulting mechanism over there, because in autonoma there is a page fault happening. From the page fault, you are seeing which page is being accessed and which CPU is trying to access them. So there, that has some overhead also. So in our cases, we always try to we always thought, or we always place pages in a way the cold pages will be always in the CXL tier. And if we can manage that, page becoming hot from the cold era is comparatively lower frequency. So that's how we actually hide the overhead of autonoma. But if there's a workload that is thrashing everything in the whole tier, all the whole tiers of memory, then we will also bear the overhead of autonoma sampling all the hot pages from the CXL memory. So in memory world, not one solution is good fit for everyone. You have to understand what's your use case, what's the behavior of the workload, and based on that you need to like come up with different solutions. And yeah.
Yeah, and that's probably true of any technology.
Yeah.
You have to have the right horse for the right course. I wonder if you can wrap up by just sort of giving us a peek at what comes next. So we are you've got the transparent page placement in the Linux kernel. At least some of the code is in there, and you're looking at moving forward with more. What do you think is coming in 23, 24, 25 on the software side for CXL support that you're excited about?
So in my opinion, like what we did is for like CXL 1.0, that's like the proof of concept that CXL works. CXL 2.0 will come with switching, one layers of switching. We can connect multiple devices there. There could be like go within beyond a machine's boundary. And with CXL 3.0, which I guess will be available in 26 or 25 time zone, there we will have multi layers of switching. That could be like a very gigantic networks of memory. So in that case, we can have do sharing, we can have peer-to-peer communications. We will have the GFM, 4,000 nodes can be like connected. So this could be a really crazy time at that period, uh, timeline. And in that case, how we are going to like manage this coherency, how we are going to like communicate between different devices like CPU, GPU, those are actually how they are going to like share memories, how they're going to like access each other's memory area. We need some support for that. And I think like right now whatever people are doing, mostly focusing on the type 3 devices, where it could be like memory extension, memory expansions. The next one is like how we can do the disaggregation within a rack scale. And this rack scale can, theoretically it can be go beyond a rack. It can be connected the whole data center theoretically, but I'm not sure whether any practical use case could be available or not, but who knows. You can like may connect the whole data center through CXS in the, and in that case all the networking problems we are facing right now will be somewhat reinvented for the memory perspective, and we may need to like handle everything what we are handling right now in the network in the memory world. So
So a lot of work to be done,
yeah.
a lot of exciting stuff happening, and the cool thing is, it works, and I think that that's the thing that we're all most excited about. So thank you so much for joining us, Hasan. It's been really, really fascinating to hear this aspect of it, because we spent most of our time on the Utilizing CXL talking to the hardware companies, and so it's great to hear a little bit about the Linux kernel support and the work that you've been doing. If people want to continue this discussion or learn more about TPP, where can they connect and where can they find it?
Yeah, so you can connect me with my LinkedIn. Like my LinkedIn handler is Hasan Al Maruf, my name. So you can like shoot me a message and ask me anything, whatever you want to know about that, or have more discussions. And yeah, you can also give me an email at hasanal@umich.edu. I'm like happy to have any chat with everyone. With
All right, cool. And as for me and Craig, you'll see us at Tech Field Day in March, where we're going to be talking to some of the CXL companies. You'll also see us here every week on Utilizing CXL. And of course, you can find us on social media, and we'll include our links in the show notes. Thank you for listening to the Utilizing CXL podcast, part of the Utilizing Tech podcast series. If you enjoyed this discussion, please subscribe in your favorite application, and please do give us a rating and review. This podcast is brought to you by GestaltIT.com, your home for IT coverage from across the enterprise. For show notes and more episodes, go to utilizingtech.com or find us on Twitter at utilizingtech. Thanks for listening, and we'll see you next week.